A spacecraft that stopped operating in 2017 deliberately crashed into Saturn's atmosphere to end its own mission on purpose, just delivered brand new evidence about one of the most promising places in the entire solar system to look for life. Nobody built a new probe. Nobody launched anything. Scientists simply went back through data that had been sitting quietly in storage for over a decade and found something nobody had noticed the first time around. It's a strange thing to sit with, the idea that some of the most exciting space news of the past year isn't coming from a brand new mission at all, but from old readings collected years ago, finally getting the closer look they deserved. Stick with me, because the story of how old data can still produce genuinely new discoveries says a lot about how patient, careful science actually works. And if you want to keep following along as this particular mystery keeps developing, go ahead and subscribe before we get into it. The moon at the center of this story is Enceladus, a relatively small, brilliantly icy world orbiting Saturn, and it has been one of the single most talked about targets in the search for extraterrestrial life for close to 2 decades now. That reputation dates back to 2005 when NASA's Cassini spacecraft, which had arrived in orbit around Saturn the year before, made an unexpected discovery while flying past this otherwise unassuming little moon. Cassini spotted geyser-like plumes of water vapor and ice grains erupting continuously from long cracks near Enceladus' south pole, jets of material shooting directly out into space. Those cracks, sometimes nicknamed tiger stripes because of how they look stretched across the moon's icy surface, turned out to be venting material with enough force that some of it escapes Enceladus' weak gravity entirely, drifting outward to form Saturn's enormous faint outer E-ring, a wide, diffuse band of ice particles that had puzzled astronomers for years before Cassini finally traced its source directly back to this one small, otherwise unremarkable moon. That single observation transformed Enceladus almost overnight from a forgettable icy speck into one of the most scientifically important moons in the solar system, because plumes, that could only mean one thing. Underneath Enceladus' frozen, reflective shell of ice, somewhere between roughly 16 and 19 miles thick, sits a genuine global ocean of liquid salt water kept from freezing solid by internal heat and constantly leaking small amounts of its contents directly out into space through those same icy cracks. Here's what makes that discovery so remarkable from an exploration standpoint. Normally, if you wanted to study what's inside a subsurface ocean on another world, you'd need to somehow drill down through miles of solid ice to get a sample. An extraordinarily difficult engineering challenge that nobody has ever actually pulled off anywhere in the solar system. Enceladus effectively does that work for us. Material from its ocean gets carried up through those cracks and sprayed directly into space, meaning a spacecraft flying through one of those plumes at the right. Altitude can sample the moon's actual ocean water without ever having to touch the surface at all. Cassini took full advantage of that opportunity, flying directly through Enceladus' plumes multiple times over the years, using onboard instruments to analyze the composition of the ice grains and vapor it collected along the way. Those flybys had already turned up remarkable results well before Cassini's mission ever ended. Scientists studying the plume samples identified organic molecules, the carbon-based building blocks associated with life as we understand it here on Earth, along with clear evidence of hydrothermal activity happening at the bottom of Enceladus' ocean, essentially underwater vents similar to the ones found on Earth's own ocean floor, where mineral-rich water gets heated by the moon's rocky core and pumped back out into the surrounding ocean. On Earth, hydrothermal vents like these are home to entire ecosystems that don't rely on sunlight at all, thriving instead on chemical energy released from the vent water itself, which is exactly why finding evidence of similar vents on Enceladus generated so much excitement among astrobiologists. If life can find a foothold around hydrothermal vents in the total darkness of Earth's deep ocean floor, there's no obvious reason. The same basic strategy couldn't work in the equally dark, equally sunlight-starved ocean hidden beneath Enceladus' ice. In a discovery that made global headlines a couple of years back, researchers also identified phosphorus in the form of sodium phosphates within those same ice grains at concentrations. Scientists estimated to be dramatically higher than typical phosphorus levels found in Earth's own oceans. Phosphorus matters enormously here because it's one of 6 essential elements, commonly abbreviated as SHNOPS, for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur that every known form of life on Earth absolutely requires. It's a genuinely critical building block, used in the backbone of DNA and RNA, in the membranes surrounding every living cell, and in the molecule cells, rely on to store and transfer energy internally. Of the 6 KNOPS elements, phosphorus had actually been the hardest one to confirm in Enceladus' plumes, and some researchers had begun to wonder whether it might simply be too scarce inside the moon's ocean to support the kind of biochemistry life on Earth depends on. Finding phosphorus in genuinely significant concentrations effectively checked off one of the last major boxes on the list of ingredients considered essential for life. at least as far as we understand life's chemistry here at home. Which brings us to the newest chapter in this story, published on October 1st of 2025 in the journal Nature Astronomy. A team led by Nozer Khawaja at the Free University of Berlin, working alongside longtime Cassini plume researcher Frank Postberg and several other collaborators, went back through Cassini's archived data and applied a smarter, more careful analytical approach than had been used before. Rather than relying primarily on older samples collected from Saturn's E ring, the vast, diffuse outer ring that gets continuously replenished by material drifting out from Enceladus's plumes over time, the team instead focused specifically on a single close, fast flyby captured back in October of 2008, when Cassini plunged directly through fresh plume material at roughly 11.2 miles per second. That speed and freshness both turned out to matter enormously. Ice grains that have spent months or years drifting through Saturn's E-ring get bombarded by radiation the entire time, which can break down or scramble more delicate organic molecules before they're ever analyzed. Grains captured just minutes after being ejected directly from the moon's cracks haven't had nearly as much time to degrade, giving scientists a far more accurate, less weathered snapshot of what the ocean beneath Enceladus's surface actually looks like chemically. Most previous studies of Enceladus's chemistry had actually relied primarily on that older, more weathered E-ring material, simply because it was more plentiful and easier to sample repeatedly, which makes this deliberate shift toward analyzing a single, fast, fresh flyby instead a meaningfully different approach, one specifically designed to catch molecules before space itself had the chance to break them down. Reanalyzing that fresher sample using updated methods, the team identified an entirely new set of complex organic compounds that hadn't been detected in any previous study of Enceladus's plumes, chemical signatures never before identified anywhere in the Saturn system. According to the researchers, these compounds are consistent with complex chemical reactions actively taking place inside the moon's subsurface ocean. And crucially, some of those same reaction pathways could plausibly continue on to produce even more complex, more biologically relevant molecules further down the line. Khawaja himself made a point of framing the stakes of this research in a way that's worth sitting with for a second. He noted that even failing to eventually find actual life on Enceladus would still count as a genuinely important scientific result, because it would raise a serious and uncomfortable question about why life doesn't seem to be present in an environment that appears, chemically speaking, to have practically everything it would need. That same month, a separate but closely related question got some fresh attention as well, this time focused not on chemistry, but on energy. For an ocean like the one hiding beneath Enceladus's ice to remain genuinely habitable over long stretches of time, rather than just briefly, it needs a stable, ongoing source of internal heat to keep it from simply freezing solid. Researchers had long known Enceladus was losing a significant amount of heat from its active south pole, the same region producing all those dramatic plumes, but a new study led by teams from Oxford University, the Southwest Research Institute, and the Planetary Science Institute in Arizona, published in Science Advances, found something nobody had confirmed before. Enceladus is also losing meaningful heat from its north pole, a region previously assumed to be comparatively quiet and geologically inactive. Finding that heat is escaping from both ends of the moon rather than concentrated entirely at one pole suggests a more balanced, more sustainable internal heat budget than scientists had previously modeled, exactly the kind of long-term stability an ocean would need in order to remain liquid and remain genuinely capable of supporting complex chemistry or biology across billions of years, rather than just a relatively brief geological moment. It's worth pausing here to give proper credit to just how unusual this entire research effort actually is from a logistics standpoint. Cassini's mission ended in September of 2017, when the spacecraft deliberately plunged into Saturn's atmosphere to burn up completely, a planned act meant specifically to protect Enceladus and Saturn's other potentially habitable moons from any risk of accidental contamination by hardware that might have still been carrying microbes from Earth. Every single one of these headline-making discoveries since then, the phosphorus detection, the newly identified organic compounds, the dual polar heat flow findings, has come entirely from scientists continuing to comb back through data the spacecraft had already collected years earlier, rather than from any new mission actively flying through the Saturn system right now. It's a genuinely striking demonstration of just how much scientific value can still be squeezed out of old data sets when researchers develop smarter analytical tools, ask sharper questions, or simply take a second, more careful look at material that had been sitting quietly on a hard drive the whole time. None of this comes without a healthy dose of scientific caution attached. And it's worth being honest about that, rather than letting the excitement run ahead of what the evidence actually shows. Finding organic molecules, phosphorus, hydrothermal activity, and a stable long-term heat source doesn't mean scientists have found actual life on Enceladus, and none of the researchers involved in this work have claimed otherwise. What they have found is a genuinely compelling case that the basic chemical ingredients and physical conditions considered necessary for life, at least based on everything we understand from studying life here on Earth, do appear to be present. Some researchers in the field have also urged a degree of caution about overinterpreting exactly what these plume samples represent, noting in separate published work that the specific chemical pathways producing some of these molecules inside Enceladus's ice grains still need to be more thoroughly understood before drawing firm conclusions about what's actually happening deep inside the moon's ocean itself, as opposed to reactions that might be occurring closer to the surface, within the icy shell or the plume material itself, after it leaves the ocean. That caution matters because it's entirely possible for chemistry happening inside the plume as freezing ice grains form and get exposed to sunlight and radiation on their way out into space to produce molecules that look organic or complex without those same reactions ever having taken place down in the actual ocean at all, sorting out which molecules genuinely originate deep in Enceladus's ocean versus which ones might be produced along the way during the plume's brief journey out into space remains one of the trickier open questions researchers in this field are still working through. That distinction actually captures the honest state of this entire field of research fairly well. Enceladus checks an impressive number of boxes: a confirmed global liquid ocean, direct physical access to sample that ocean without drilling through miles of ice, organic molecules, evidence of hydrothermal activity. Now, a plausible long-term heat source capable of keeping that ocean liquid for potentially billions of years. But every one of those findings describes conditions that appear favorable for life, rather than direct evidence of life itself, and closing that particular gap is going to require considerably more than analyzing archived data from a spacecraft that finished its mission back in 2017, which is exactly why attention is now turning toward what comes next. Momentum has been building around proposals for a dedicated new mission specifically designed to return to Enceladus and search directly for biosignatures, actual chemical or physical evidence of biological activity, rather than simply the raw ingredients. Biology would need to get started. European space agencies have been actively developing concepts for exactly this kind of follow-up mission, aiming to fly a spacecraft equipped with considerably more sensitive instruments directly through Enceladus's plumes, or potentially even land on its icy surface near the active south pole, specifically hunting for the kind of definitive evidence that archived Cassini data, however cleverly reanalyzed, simply isn't equipped to provide on its own. It's also worth noting that Enceladus isn't operating in a vacuum here, so to speak, in terms of scientific attention. Researchers studying this same phosphorus-rich chemistry have pointed out that similarly favorable conditions might well exist in the hidden oceans of other icy worlds too, including Jupiter's moon Europa and Saturn's own largest moon, Titan, both of which are also believed to harbor subsurface liquid water and are already targets of their own dedicated exploration efforts. Enceladus simply happens to have the distinct advantage of spraying its ocean directly out into space where a passing spacecraft can sample it, giving it something of a head start over these other candidates in terms of how directly scientists can actually study what's hiding beneath the ice. Scientists involved in the current research have been fairly direct about what needs to happen next, describing the logical follow-up step as sending appropriately equipped instruments back to Enceladus, specifically to search for genuine organic biomarkers, the kind of unambiguous chemical fingerprint that would move the story from a compelling circumstantial case toward something considerably closer to an actual answer. So here's where all of this actually lands. More than a decade after a spacecraft that no longer exists finished its mission by deliberately burning up in Saturn's own atmosphere, scientists went back through its archived data and found entirely new organic compounds inside fresh plume material, alongside separate evidence that Enceladus's hidden ocean has a more stable, longer-lasting heat source than previously understood. None of it proves life exists there. All of it strengthens an already remarkably compelling case that if life were ever going to exist somewhere else in our own solar system, this small icy moon quietly orbiting Saturn remains one of the single most promising places to actually go looking. If you want to keep following along as momentum builds toward an actual return mission, and as researchers keep pulling new discoveries out of old Cassini data in the meantime, make sure you're subscribed with notifications turned on, drop a comment letting me know whether you think Enceladus is hiding something down in that ocean, and share this with anyone you know who'd be amazed to learn one of our best shots at finding alien life might already have all the right ingredients sitting there, waiting.